All right, so a majority of chapter 6 is on forces and friction, right? However, there is the final bit of chapter 6 on uniform circular motion, right? Because we will deal with objects swinging back and forth as a pendulum, for example, or driving through a loop to loop, right? And we'll need to deal with this circular motion aspect. I skipped over this way back in chapter 4 because I wanted to do it all and introduce it all at one time, which is now. Okay. So, what does uniform circular motion mean? Well, it's somewhat self-explanatory, but it's when objects move at constant radius and at constant speed, they undergo some form of uniform circular motion. Uniform referring to their speed and radius. They don't always have to undergo an entire circle, right? They can just move throughout part of a circle, but it's okay. For lack of a better example, we'll just use an entire circle. So let me use actually black. So let's say there's some object's path of motion. And so when this object is at the bottom, say this is a top-down view, for example, when it's at the bottom, it has some instantaneous speed, right? Or its tangential speed. We'll call that v, okay? And actually, in this case, it's important to talk about its velocity as well. Okay, so we'll call that velocity 1. A short time later, it may be moving at the same speed. I'm going to try and draw those equal in magnitude, right? Such that their speeds are equal, but the velocities are not. So that would be velocity 2. Remember, vectors have a magnitude and a direction. In this case, the magnitudes of v1 and v2 are equal. They haven't changed. However, the direction has changed. That means that it's a totally new vector, right? And because this is an object's velocity, because that changes, what do you call the type of motion, or what do you call it when a velocity changes? That's an acceleration, right? So let me do it in black here. So the acceleration is defined as a change in velocity over a change in time, right? Written another way, v2 minus v1 over, well, t2 minus t1, or let's just call it t, right, over some time. So in our example here, it's a very short time, right, from when the particle was at, say, the very bottom to, well, just past the very bottom. So that's a very short time. Let's actually draw these vectors head to tail, right? Let's graphically represent this. So I'm going to literally show you which direction that acceleration changes or points. Okay, so I'm going to take v2, I'm translating it over here, kind of like that, somewhat. That's v2. And now we have v2 minus v1. Notice v1, positive v1, points horizontally to the right, or directly to the right. But we have negative v1, so that points directly to the left. And so we do that from the head of v2. And we have that, right? I simply put the vectors head to tail. I graphically wrote that expression right there, v2 minus v1. And so the resultant is right there in red, right? That's the change in velocity. Well, that's exactly what the acceleration is, right? So in other words, what we have there is the acceleration vector. And now I'm going to translate that acceleration vector in red back to the tail of V2 on the circle here. So I'm going to try and do it something like that. Look at which direction that points. It points exactly towards the center of the circle, somewhere right there. And so this is known as the centripetal acceleration. Centripetal, not to be confused with centrifugal. Okay, centripetal acceleration. So we can write that as A with a subscript C. That's how most books write it. Okay. So this is not the same as linear acceleration. Right? AC is not the same as simply A or A tangential, if you will. Right? It's specifically referring to a change in velocity for an object moving in an arc at a constant radius. I didn't draw the radius, but that's a radius there. And if you were to draw it right there, that would be the same radius. Okay? So two different types of acceleration, right? Now, this is a new type of acceleration to take into account. Okay? I mentioned centripetal is not the same as centrifugal. Okay, let me write that. Not the same as centrifugal. This gets 2 exclamation points. Okay, not the same. Centrifugal is not really a force at all, right? It's not really an acceleration at all. It's the apparent force that you feel when moving it in a circle, right? Say if you're getting on the highway, right, and you take that on ramp and you take the steep curve, right, upwards or downwards, and there is an apparent force on your body. You feel your body moving outwards away from the center of that circle or arc, right? That apparent force is or has come to be known as the centrifugal force, and it's not a real force. Don't use it in your problems. If you do, I will draw funny pictures and laugh at you inwardly. Okay, it's not the same as centripetal. Centripetal you will deal with in your problems, right? That is an actual force. And so what I've drawn here in red is the acceleration. Well, you can also draw the force. I guess it's the same vector. You can also draw the centripetal force, F sub C. Okay? So now, in your book, the centripetal force has an expression of mass times centripetal acceleration. Okay? In chapter 4, if you would like to go back and look at the derivation for A sub C, they get V squared over R. Right? It's a incredibly brilliant derivation, right, of how they get V squared over R. Notice this is the speed, right? It's an unvectored V. Mass times speed squared divided by the radius of the arc or circle. This is the centripetal force, okay? So, again, not to be confused with centrifugal, right? That's the apparent force outwards. It's not real, okay? So, one more thing. If an object undergoes a centripetal force, a centripetal acceleration is moving at a constant speed, constant radius, all that stuff, right? That means if it undergoes a complete circle, it has to take some time to do that, right? So distance equals rate times time. We know that from, well, chapter 2. Distance equals, I'll say, rate times time, v times t. The distance of a circle is simply the circumference. So 2 pi r equals v, and in this case, we write time as a capital T. I know, you're used to capital T being a tension. I know it. When doing uniform circular motion problems, capital T is known as the period, right? It's the time to complete one cycle or one complete revolution. Okay. So it is what it is. I know. So, okay. This is the distance equals rate times time. And so if you wanted to, you can solve for the speed this way as well. This is the, again, linear speed, v here, linear speed, as is this, right? That's also the linear speed. So v equals 2 pi r over t. Notice the units. The units are 2 pi's in radians, so that's really unitless. R is in meters, that's a distance, and t is in seconds because it's a time. So the overall units of this is still meters per second, and we're good. When doing uniform circular motion problems, there is another variable to deal with, and that's known as the angular speed. So this here is the linear speed, right, with units of meters per second. There's also an angular speed, which is known as omega, right? The Greek letter omega. Actually, let me write that out. So the angular speed is not a W, it's omega. Okay, and so the angular speed is a distance per time, right? But in this case, it's an angular distance per time. So the units here are radians per second. And so radians we have, well, 2 pi, and seconds we have the period t. So the units are radians per second. Okay, so you can combine these two speed equations and get a relationship. Quickly running out of room, let me do that up here. We have v equals omega r, right? This is another way to relate the linear speed to the angular speed, and you do that by the constant radius. Okay, so I hope this was a quick overview of uniform acceleration for you. In the last video, I will do an example of uniform acceleration with centripetal forces with an actual free body diagram analysis. Okay, so with that, I hope you have enjoyed it. Thanks for watching.